And what is that? That's the question we keep trying to answer here.
Hello, and thank you for watching my video. This is called Quadratic Polynomial Number Theorem, and it is a generalization of Euler's pentagonal number theorem, and we'll see what that means for known results, and we'll look at some new things too. And this is a submission to 3 Blue, 1 Brown's Summer of Math Exposition 1, SOME1. Thanks, Grant. This guy and gang for inviting me.
Euler's pentagonal number theorem is expressed with an infinite limit, always. And the reason being is that as we come down to finite, this equality is no longer true. As you multiply in more and more factors of your product, you're going to get a certain number of accurate sequence elements, and you're going to get all the stuff that follows. What we want to do is take this approach where we're going to look at sort of the guts and the structure that happens along the way. This LR is the length of the partial products at each k, successive k, as we saw before. And the asterisk on pk is because it's only valid up to the first r, well, not exactly the first r elements, but it's only valid up to a certain number of elements. And the LR is the sum of the factors themselves. So if you have factors spaced other than every other one, this R will still remain the number of factors, and the actual LR can grow very large if the factors have a wide distribution. I've written something similar for the inverse of this sequence, and I put this capital I star because the inverse and the data that you have in this sequence is intimately related to the data that you have in this sequence, and one is alternating, one is apparently, and it is, strictly non-decreasing. So this star basically indicates that it is the finite sequence. So what we actually want to say is this is IP, where I, it is for inverse. But it's also useful to think of it as an indicator sequence. Inverse, indicator, I, and we'll add this subscript P here to indicate that this is the indicator sequence of, or the inverse sequence of the partitions sequence. So we've done this one here for r equals 1 plus q to the k, and though it seems to have this form, it's actually the non-decreasing type, and so we might suspect that this one here will look sort of like more like an indicator sequence, and that if there is anything to this, which there is, we can play this notion of indicate what is this indicating versus what are we getting on this side, and we can play these two sides across each other, the inverse and the and what we would call the divergent. So, and yeah, and of course that's exactly what we get. And in this case, we are getting more than just a -1 or a +1. We're actually getting some accumulation here. This one will never have anything but ones, -1s, and zeros because that quadratic equation ensures it. Right off the bat, this isn't quadratic. For right now, it doesn't tell us. We want to find what is the equivalent summation form here, and then also for this one. Okay, so to answer the question on what this function might be, we want to shift to Euler's PNT mode where we're working at the infinite limit. There are a couple of really good tricks that can be used, and in combination you're able to do some very clever things. And the first one is to manipulate the term in place. So if we manipulate this term in place, one thing we can do is we can say that 1
plus q to the k multiplied by 1 minus q to the k will give us 1 minus q to the 2k.
So we can substitute 1
Plus q to k equals 1 minus q to the 2k over 1 minus q to the k.
And now we can do the, well, it's not quite the second trick, but it's the first step of the second trick that we'll use next, which is to, in this product, separate this into 2 or more factors. And in this case, let's just separate it into the numerator and the denominator so that we have product. Excuse me, I rewrote that one. I meant to write that one. Bubble ball. That the product k equals 1 to infinity of this, and that's product 2. That can be written equal to
k equals 1 to infinity of 1 minus q to 2k times product of k equals 1 to infinity of 1 over 1 minus q to the k.
And now is when we can apply the second step of the second trick, which is to actually split one or more of these into 2 factors based on assigning the exponents of q into subsets. So in this case, we want to do it for this one right here. And we're going to leave this term as is, and let's split this one into a product of over k, the natural numbers, but in 2 sets. So we end up with, and we're going to say that this is the product over k such that k is equivalent to 0 mod 2, aka the even natural numbers as we go to infinity. For now, keeping this term the same, 1 over 1 minus q to the k. That the odd ones will be avoided is implicit in this restriction on the index. So then we can say, then multiply in the odd ones, k such that k is equivalent to 1 mod 2 of 1 over 1 minus q to the k. Then we can rewrite, or what is commonly done is to rewrite this over a full index, so that and do it by then changing the exponent on the q in the term expression, and what we get is
The same thing here, times product k equals 1 to infinity of 1 over 1 minus q to the 2k times product k equals 1 to infinity of 1 over 1 minus q to the 2k minus 1.
so all of the odd exponents, all of the even exponents. However, do note that had we kept this notion of a finite limit, that if this were going to R, that when we got to R, we'd be multiplying in 1 minus q to an exponent of with 2r. So it introduces these higher factors, and that is why it's not going to be equal. One of the reasons it's not going to be equal at the finite limit. Euler's P&T is only true at the infinite limit, and only in the sense of that the two sides and the product expression both generate the same sequence. And here's how that is proven, is by then noting that this is 1 minus q to 2k. So that cancels with that, leaving us this. So that's interesting. Now I could write this out on a card, but let's show where this. Let's show another connection that gets us to this. So for that, we're going to want to start with partitions of n. This one here, only we're going to be thinking of it in terms of the infinite sense. If we do the same thing we just did, then we end up with, so what is this sequence here for the even parts? Well, I forgot our 1 in here. For any odd number, we can't have a partition of even parts because the even parts will sum to an even number. So we can forget about anything that's odd. For 4,
we have 4 and 2, 2. For 6, we have 6 itself. 4, 2, nope, 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 yep, no. 7, no.
So this sequence is going to be starting 1,
0, 1, 0, 2, 0, 3, and 0.
I'm going to do a couple more. For good measure. No, well, we won't do 9. We'll just do 10 because 9 we know is 0. And let's check that. And we get 42, which is correct. For 8, we have, for the even ones, we have
8, 6, 2, 4, 4, 4, 2, 2, no 3s, 2s, and 2s. And for 10, we have 10, 8, 2, 6, 4, 6, 2, 2, no 5s, 4, 2, 2, these all have 1s, so no, these all have 3s, so no.
And that's our only one left. So this sequence then,
If that's 3, 0, 1, 2, 3, 4.
5, and then 1, 2, 0 for 9, 7, dot, dot, dot. From what we did before, we know that this sequence has to be the sequence of the number of partitions into odd parts. So let's just confirm that. And 10. So those are all consistent with what we've got here. So this is the number of partitions into odd parts. And of course, obviously we note and notice that A, they're mutually exclusive, even parts, odd parts, and that the sum of them is going to be less than the number of partitions. But when we multiply, if we were to multiply these two Q series together, then we're going to recover this and get the full count. But for now, we're just going to carry on with what Euler and others proved a couple hundred years ago. The first statement of which is that the number of partitions into odd parts is equivalent to this. So is this partitions into odd parts, or is there some other characteristic going on here? And if we can find some other characteristic going on here that these numbers account for, then we have a relationship. And that's one of the first identities Euler proves, is that they count the same, but that is no way to say that they're counting the same sets of partitions. For the even case, 1 minus q to the 2k, we get this sequence, which is intermittent with these zeros, but otherwise non-decreasing. And in fact, you may know or you may have noticed that the numbers that come in between are actually the partition numbers themselves. It's not a casual coincidence there. This actually does do that. So, and then in this one here, now we've got our 1 minus q to the 2k minus 1 over that quantity product here, and that gives us this sequence, which is the same sequence. So what we just found is then confirmed by this exercise of getting this sequence. So does that mean that this is that this function that we're trying to find right here is the number of partitions into odd parts? It's not. Both generate this sequence, but they do it differently. So these sequences, bear in mind, are counting. It's a counting function. So what we're getting is we're getting different things that are equivalent in number. And it's this correspondence that is known as Euler's partition identity. One of the first things he proves with the pentagonal number theorem is that the partitions into odd parts given by this Q series are equivalent to another type of partition in terms of being equal in number. And what is that? That's the question we keep trying to answer here. So we know this one is, at least we know, number of partitions into some kind of parts. So we can figure we're going to have a p here, and it's just down to what is the subscript that goes in here that defines what they are. And once we know that, then we can relate it back to its indicator sequence, aka its inverse. And the answer lies with the geometric series identity. Okay, by the geometric series identity, 1 minus q to the d for any degree, integer degree, over 1 minus q equals 1
plus q squared.
q to the d minus 1. And that's obvious because you end up with one copy here and then minus q times a copy of that, place one below. Same thing we were doing before, just take out the q's. So if d is equal to 1, then we have 1
Minus q over 1 minus q. And it equals 1.
and that's boring. So if we had d equals 2, we have 1
Minus q squared over 1 minus q.
which is of course our 1 plus q. If d were to equal 3, then we'd have 1 minus
Q to the 3 over 1 minus q equals 1 plus q
squared. And if we had take this term into our product, then we're going to have a k for each one. So it's as k goes over the natural numbers in this product, any individual k over out of the positive integers is only going to be counting once. And here, when we take this product out, you can have it'll count once, it'll count twice.
Okay, this section was my second attempt to explain in a clever way that when you take the quantity 1 plus q to the k plus q to the 2k and use that quantity as the term in your product Q series product, that it results in all of the k, all the natural number k's being counted once, and because of the Q2k, all of the even natural numbers in terms of your indicator sequence are going to get pinged twice. And also then in combination with the odd ones, the odd numbers are going to get pinged twice. But no more than that. So it results in a restricted partition set where no part has more than 2 repeated parts. And that was the entire point of whatever it is I'm doing here. It went sideways. Anyway, but it's as simple as what I've just said, and picking up from there, now we're going to work back to with just one distinct part.
Is that with our expression of 1
plus q squared equals 1 minus q cubed over 1 minus q,
that we're getting partitions into parts with partitions with no more than 2 repeated parts. By that argument and by this, when you have the original one that we are investigating, 1 plus q, that's going to translate into
partitions into parts where no part is repeated, aka
into distinct parts. And actually this argument works a heck of a lot better with the degree equals 1 because look at it, we get 1.
We essentially have 1 q, 1 q squared, 1 q cubed, etc.
So we've only got 1 of each to choose. If we're going to have a number that appears as a count within our sequence, then it has to have been able to be composed by individual distinct integers. So for 4, we're going to have 4 plus 0. We're going to have 1 plus 3 plus 1. But we can't have 2 plus 2 because 2 only appears ever once. So there's no other 2 out here to marry with it. From there, we get 4 and 3 plus 1. We can't do 2 plus 2. We can't do 2 plus 1 plus 1, or much less 4 ones. This is degree 2. When we go down to degree 1, this is going to drop to 2. So you can see how these partitions become restricted. Okay, so we can now call this what it is, number of partitions into distinct parts. And our function here is designated with P and then a subscript capital D. Here, partitions into odd parts. So we've got unrestricted partitions, partitions into distinct parts, partitions into odd parts, partitions into even parts. I'm using infinity on this one, aren't I? Yeah, let me rewrite both of these. So we have unrestricted partitions here, and then its indicator sequence, aka its inverse. This number part can be split into number of partitions into even parts. We use a little capital or a large squiggly E. Partitions into odd parts, a P and a little funny capital O. That's the function. And of course, partitions of n into odd parts are equinumerous with the partitions of n into distinct parts. Let's show that real quick. Empty set. Okay, so if we're going to look at partitions in distinct parts, we have 1.
Here 2 is the only distinct part, the one with distinct parts. Here we have 3 and 2, 1. Here we have 4, 3, 1, nothing else counts. 5, 4, 1, 3, 2, and all these have repeated parts. Repeat, repeat, no repeat, 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 repeat.
Okay, so into distinct parts we have 1, 4, and into odd parts, well, we have 1 there.
1 there, 1 there, and 1 there. There, and there, and then there, and there, and 5, 1.
Not that. Bar.
3, 3, 3 and all ones, and all ones.
So 1.
1, 2, 2, 2, 3, 4 in the red.
So that's how that works out. This is Euler's partition identity. And the result of that is that this sequence is going to be the same. Each one's not going to eke it out the same way, at the same rate. That's part of why they're counting different sets of partitions. Coming back to this one, the inverse of the generating function, or the Q series for partitions into distinct parts, is the indicator I of P of D of N. We'll call that that sequence that, and we're going to get this is equal to
K equals 0 to LR minus 1, I, P, D, capital D, star, of K dot Q to the K.
and
As R and LR go to infinity.
we're going to get that sequence there. So this whole idea of indicator sequence is that there's information here that is related to this, and how these two talk to each other is what is of interest. How do we decode an indicator sequence? I am grateful to the Summer of Math Exposition project and the idea of it, that here's a place where we can informally share mathematical teachings and information and research in a less formal environment, without a bunch of poppycocking and hogwashing. And so I appreciate the opportunity to show what I've got going on, and that's it. Thank you very much for watching my video.